Welcome back to part 2 of the presentation on multi-area OSPF. This presentation was developed by Lonnie Decker and Elaine Horn and will be presented by Elaine. In this part of the recording, we will be reviewing multi-area OSPF implementation and discussing the types of LSAs exchanged between areas. So let's begin the presentation with a discussion of multi-area OSPF implementation. OSPF can cause issues in large networks due to frequent SPF algorithm calculations. In a large network, changes are inevitable, so the routers spend many CPU cycles recalculating the SPF algorithm and updating the routing table. So you're going to notice in the picture, if you look at the top router, the router up here in area 0, it says the SPF is running too often for me to route. So that algorithm is running so much that it can't even route packets. Another issue can be large routing tables. OSPF does not perform route summarization by default. If the routes are not summarized, the routing table can become very large depending on the size of the network. And that one you might refer to this bottom router where it says my routing table is too big and I am running low on memory. There can also be an issue with large link state databases, sometimes referred to as LSDBs. Because the link state database covers the topology of the entire network, each router must maintain an entry for every network. The solution: to make OSPF more efficient and scalable, the network can be divided into multiple OSPF areas. An OSPF area is a group of routers that share the same link state information in their link state databases. In this topology, notice it has been broken into 3 areas. The advantages of breaking these into areas into multi-area OSPF is that you will have reduced frequency of the SPF calculations. It's going to localize an impact of a topology change within an area. It's going to minimize the routing update impact because the link state advertisement flooding stops at the area boundary. So what will happen is, notice you've got an area 0 here and area 1 here. Area 1 routing updates or the link state advertisements will be stopped at the boundary right here between area 1 and area 0. Another advantage is that there will be smaller routing tables. There are fewer routing table entries as network addresses can be summarized between areas. For example, area 1 would summarize its routes and send them to area 0. So they would get a summary, would just send a summary over here to area 0. There will be reduced link state update overhead, and this will minimize processing and memory requirements because there are fewer routers exchanging link state advertisements. Here we have an implementation of multi-area OSPF with 3 areas. Notice there's an area 1, an area 0, and an area 51. The result is smaller routing tables and less link state advertisements. SPF is only run within an area if there is a change in the network. And you might want to take a look down here at router 2. Notice how the little comment box here says, I now only need to run the SPF algorithm when there is a change in area 0 or area 51. So since this router has an interface in area 0 and interface in area 51, it will have to run an SPF algorithm when there's a change in area 0 and area 51, but it will not have to do any SPF algorithm changes when there's a change in area 1. Multi-area OSPF is implemented in a two-layer area hierarchy. There will be backbone areas and regular areas. The backbone area is sometimes known as a transit area. And hierarchical networking defines the backbone area or area 0 as the core to which all other areas directly connect. So you will see in our picture that right here is area 0. This would be considered the backbone area. Backbone areas interconnect with other OSPF area types. And an OSPF backbone area's primary function is the fast and efficient movement of IT packets. Generally, end users are not found within a backbone area. There are also regular areas, and that will be these other two areas, Area 1, Area 51. Those will connect users and resources. Regular areas are usually set up along functional or geographical groupings. By default, a regular area does not allow traffic from another area to use its links to reach other areas. All traffic from other areas cross area 0. There are 4 different types of OSPF routers. There's internal routers. So if we look at our picture, you're going to see there's internal routers in area 1. There's internal routers in area 2. And there's internal routers in area 0. This is a router that has all of its interfaces in the same area. All internal routers in an area have identical link state databases. So if we look in area 1, these are internal because all their interfaces are in area 1. And they all have identical link state databases because they're in the same area. A backbone router, this is the router that's in a backbone area. So if we look at our picture, any router that's in this area is a backbone router. So there's 4 of them. There's 2 here. And then these 2 will be counted as backbones as well because they do have interfaces in the backbone. Generally, the backbone area is set to area 0. There's area border routers, which sometimes we shorten and just call those ABRs. This is a router that has interfaces attached to multiple areas, such as the 2 right here. So there's one here, and there's one here. It must maintain separate link state databases for each area it is connected to and can route between areas. ABRs are exit points for the area, which means that the routing information destined for another area can get there only via the area border router of the local area. Area border routers can be configured to summarize the routing information from the link state databases of their attached areas. So it would be very common that all of these routes in here would be summarized before sending them on to area 0. ABRs distribute the routing information into the backbone. The backbone routers then forward the information to the other area border routers. In a multi-area network, an area can have 1 or more area border routers. So you're going to notice in our picture we have 2 of them. The last type of router is an autonomous system boundary router. You're going to see that's pointed to down here in the picture. This is a router that has at least one interface attached to an external internetwork, another autonomous system. So notice down here we've got an external autonomous system. That's going to make this an autonomous system boundary router. This autonomous system will be a non-OSPF network. An autonomous system boundary router can import non-OSPF network information to the OSPF network and vice versa using a process called route redistribution. Redistribution in multi-area OSPF occurs when an autonomous system boundary router connects different routing domains and configures them to exchange and advertise routing information between those routing domains. So if we were running EIGRP in the external autonomous system and we wanted those routes to be shared with our OSPF domain, then they would have to be redistributed into OSPF. A router can be classified as more than one router type. For example, if a router connects to Area 0 and Area 1, it is a backbone router and an area border router, which we see that right here, that this router is an ABR and a backbone router. The next part of our presentation will cover types of LSAs exchanged between areas. This is a chart that you have seen before. We used this when we were discussing single area OSPF. Recall that there are 5 packet types used by OSPF: the hello, the database description, the link state request, the link state update, and the link state acknowledgement. For OSPF, type 4 link state update packets, so concentrate on the link state update packets. There are 11 different link state advertisement types used by OSPF, but only types 1 through 5 are covered in CCNA. So if we look at those link state updates, there are 11 different types of link state advertisements. All link state advertisement types are delivered in a type 4 OSPF packet. So again, we see type 4 link state updates. Those link state updates can be 1 through 11 different LSA types. The ones that we're going to concentrate on are types 1 through 5. So these are the areas of concentration. LSA type 1 is considered a router LSA. Type 2, a network LSA. Type 3 and 4, summary LSAs. And type 5 is an autonomous system external LSA. And we're going to spend some time right now talking about each one of those. As shown in the figure, all routers advertise their directly connected OSPF-enabled links in a Type 1 link state advertisement and forward their network information to OSPF neighbors. The link state advertisement contains a list of the directly connected interfaces, link types, and link states. Type 1 link state advertisements are also referred to as router link entries. The Type 1 link state advertisement link ID is identified by the router ID of the originating router. Type 1 link state advertisements are flooded only within the area in which they originated. So you're going to notice all routers generate type 1 link state advertisements. And again, link state advertisements are flooded within the area and do not propagate beyond an area border router. Now, something that we'll see in just a few minutes is that the area border routers will advertise the network learned from these type 1 link state advertisements to other areas as type 3 link state advertisements. So we'll see that in just a second. A type 2 link state advertisement only exists for multi-access and non-broadcast multi-access networks such as Ethernet and frame relay, where there is a designated router elected and at least 2 routers on the multi-access segment. The designated router floods type 2 link state advertisements only within the area in which they originated. Type 2 link state advertisements are not forwarded outside of an area. As shown in the figure, area border router 1 is the designated router for the Ethernet network in area 1. So we're looking right here. It generates the type 2 LSA and forwards it into area 1. So it's going to forward that into area 1. ABR2 is a designated router for the multi-access network in area 0. There are no multi-access networks in area 2, so no Ethernet or frame relay over here. And therefore, no type 2 LSAs are ever propagated in that area. And again, only a designated router generates a type 2 LSA. Type 3 LSAs are used by area border routers to advertise networks from other areas. Area border routers collect type 1 link state advertisements in the link state database. So you're going to notice we see that happening right here. This area border router is collecting these type 1s. Notice these are internal type 1s. The ABRs collect type 1 LSAs in the link state database. After an OSPF area has converged, the area border router creates a type 3 LSA, so you see that's happening right here, for each of its learned OSPF networks. Therefore, an area border router with many OSPF routes must create type 3 LSAs for each network. So notice down here it says a link state advertisement is required for every subnet. The area border routers flood type 3 LSAs to other areas and are segmented and regenerated by other area border routers. As shown in the figure, ABR1 and ABR2 flood type 3 LSAs from one area to other areas. The area border routers propagate the type 3 LSAs into other areas. In a large OSPF deployment with many networks, propagating type 3 LSAs can cause significant flooding problems. For this reason, it is strongly recommended that manual route summarization be configured on the area border router. And don't forget, OSPF by default does not summarize. So later on in the presentation, you will learn how to summarize the networks. Receiving a Type 3 link state advertisement into its area does not cause a router to run the SPF algorithm. The routes being advertised in the Type 3 link state advertisements are added to or deleted from the router's routing table, but a full shortest path first calculation is not necessary. Type 4 and Type 5 link state advertisements are used to identify an autonomous system boundary router and advertise external networks into an OSPF routing domain. So let's look at the Type 4 first. So the Type 4 summary link state advertisement is generated by an area border router only when an autonomous system boundary router exists within an area. So you're going to notice in our graphic, we're going to see that there's an autonomous system boundary router here. It's going to send a Type 1 LSA. This area border router is going to recognize that that's coming from an autonomous system boundary router, and it's going to send a Type 4. A Type 4 summary link state advertisement is generated by an area border router only when that autonomous system boundary router exists within the area. A Type 4 link state advertisement identifies the autonomous system boundary router and provides a route to it. All traffic destined to an external autonomous system requires routing table knowledge of that autonomous system boundary router that originated the external route. And just as a review, as shown in the figure, area border router 1 sends Type 1 link state advertisement router identifying itself as an autonomous system boundary router. The link state advertisement includes a special bit known as the external bit that is used to identify the router as an autonomous system boundary router. When the area border router 1 receives the Type 1 link state advertisement, it notices the bit. It builds a Type 4 link state advertisement and then floods the Type 4 link state advertisement to the backbone area. Subsequent area border routers flood the Type 4 link state advertisement into other areas. Type 5 external link state advertisements describe routes to networks outside the OSPF autonomous system. So notice what the difference is here. There is an external autonomous system sitting out here. Type 5 external link state advertisements describe routes to networks outside the OSPF autonomous system. Type 5 LSAs are generated by the autonomous system boundary router and are flooded to the entire autonomous system. So notice these Type 5s are coming right from that autonomous system boundary router. Type 5 LSAs are also referred to as autonomous system external LSA entries. In the figure, the autonomous system boundary router generates Type 5 link state advertisement for each of its external routes and floods it into the area. Subsequent area border routers also flood the Type 5 link state advertisement into other areas, and you can see that happening on the picture. Routers in other areas use the information from the Type 4 link state advertisement to reach the external routes. So you're going to notice there's some work here happening between type 4 and type 5. So notice the type 4 link state advertisement is needed for the other routers to find the autonomous system boundary router, or the ASBR. In a large OSPF deployment with many networks propagating multiple type 5 link state advertisement can cause significant flooding problems. For this reason, it is strongly recommended that manual route summarization be configured on the autonomous system boundary router. So these are 5 types. Let's see what the routing table looks like. Routing table entries for OSPF networks will be identified in the routing table based on the area in which they originated in comparison to the router displaying that route. So you're going to notice that the route designators, we will have O's, which refer to OSPF intra areas, and network LSAs. Those are your type 1s and type 2s. There will be some labeled O, IA, and those will be your OSPF inter areas. Those will be type 3s and 4s. That's your summary LSAs. And then your external routes will either be O with an E1 or O with an E2. Now, the O space IA, that's for IP version 4. If we're running OSPF version 3, which is for IP version 6, that's just going to be an O and an I. So you'll see that in one of our examples. So that's a little bit different on IP version 6 versus IP version 4. The routing table shows a multi-area OSPF topology with a link to an external non-OSPF network. OSPF routes in an IP version 4 routing table are identified using the following descriptors. O, and we've kind of talked about this on the next slide, on the previous slide, so we'll just review it again. O is router type 1 and network type 2 LSAs. Describe the details within an area. The routing table reflects this link state information with the designation of O, meaning the route is intra-area. Notice down here we've got the O space IA. When an area border router receives summary LSAs, it adds them to its link states database and regenerates them into the local area. When an area border router receives external link state advertisement, it adds them to its link state database and floods them into the area. The internal routers then assimilate the information into their databases. Summary LSAs appear in the routing table as IA or inter-area routes. OE1 or OE2 are external LSAs appear in the routing table marked as external type 1 or external type 2. And you're going to notice here we have one that says OE2. So that's our external route. This figure displays an IP version 6 OSPF routing table with intra-areas, inter-areas, and external routing table information. And notice how the inter-area ones, the summary routes, are labeled OI. And again, if we're using IP version 6, that is known as OSPF version 3. For external routes, most of what we'll see in CCNA is E2. Those are the default. Notice it says the cost of OE2 packet routes is just the external cost. It says use this type if only one autonomous system boundary router is advertising an external route to the autonomous system. So most of the time in our topology, that's what we're going to see. Notice the difference between the two is the second one will add the internal cost of each link as well. Most of what we'll see is E2s. Each router uses the SPF algorithm against the link state database to build the SPF tree. The SPF tree is used to determine the best paths. As shown in the figure, the order in which the paths are calculated is as follows. All routers calculate the best paths to destinations within their areas. Those are your intra areas. And that these entries to the routing table. These are the type 1 and the type 2 link state advertisements, which are noted in the routing table with a routing designator of O. Step 2, all routers calculate the best paths to other areas within the internetwork. These best paths are the inter-area route entries, or type 3 and type 4 link state advertisements, and are noted with a routing designator of O space IA. Step 3, all routers calculate the best paths to the external autonomous system, type 5 destinations. These are noted with either an OE1 or an OE2 route designator, depending on the configuration. If you've done all your configuration correctly, when converged, a router can communicate with any network within or outside the OSPF autonomous system. And this is the end of this part of the recording. Please listen to part 3 of the recording, and in addition, after you get done listening to the entire recording based on the PowerPoint, you will find that Lonnie Decker has a packet tracer activity for you and also a recording of a demonstration of OSPF. So please listen to part 3 and then also look for Lonnie's presentation that's a packet tracer activity. Thank you.